Good morning. Today we have to see one more concept, that is induced EMF. Induced EMF due to flux of field. Due to flux of field. Induced EMF due to flux of field. Now see, consider a small area. Consider a small area, yes, situated in magnetic field. Suppose this one as magnetic field like this. Suppose this one as magnetic field. Consider a small area. Consider a small area, yes, situated in magnetic field of induction B. If suppose theta, that is angle between direction of magnetic field with a vector area of field, that is dA. Suppose this one as small area of that field. If theta, that is angle between, if theta the angle between direction of magnetic field and vector area dA, then magnetic flux passes through small area dA, that is d phi is equal to b dot dA. B dot dA, which is nothing but magnitude of vector B, magnitude of vector area dA into cos theta. This is small magnetic field. Small magnetic flux due to small area, and therefore total magnetic flux, comma phi is equal to integration of d phi, which is equal to integration of b dot dA over total surface area, yes, and hence induced EMF in flux of field E is equal to minus d phi by dt. Therefore E is equal to minus d by dt integration of b dot dA over closed interval. This is about induced EMF in flux of field. Okay. See once more. Consider a small area. Consider a small area, yes, situated in magnetic field. If theta, let consider a finite area, yes. Consider a finite area, yes, situated in magnetic field of magnetic induction P, magnetic field will not remain constant, and hence we have to consider small surface area. Small area as magnetic field across this finite area will not remain constant. We have to consider small surface area dA. Let theta, angle between direction of magnetic field with vector area of area dA, then magnetic flux passes through area dA. d phi is equal to magnetic flux, magnetic induction into area. डॉट प्रोडक्ट आहे म्हणून या ठिकाणी cos theta घेतलं. This is small magnetic flux due to small area, and therefore total magnetic flux over finite area ds integration, and hence induced EMF becomes minus d phi by dt, value of phi, integration of b dot dA. Finite area, yes. Now we have to see one more term, that is motional electromagnetic force. Motional electromotive force. Motional electromotive force. Motional electromotive force. Consider a rectangular frame. Consider a rectangular frame of wire. Consider a rectangular frame of wire A, B, C, D. Consider a rectangular wire frame ABCD placed in uniform magnetic field. Placed in uniform magnetic field like this. Placed in uniform magnetic field. Placed in uniform magnetic field which is perpendicular to plane. Suppose this one as a uniform magnetic field. Suppose this one as a uniform magnetic field of magnetic induction P. Consider a rectangular wire frame. Consider a rectangular wire frame ABCD situated in magnetic field. Let L, that is length of frame, L, that is length of frame, let's suppose L, that is length of frame, X, that is breadth of frame, B. magnetic induction of uniform magnetic field, N. length of frame, X. breadth of frame, B. magnetic induction of uniform magnetic field. Then area of frame in magnetic field. In magnetic field, that is A is equal to L into X, length into breadth, हा झाला area, and therefore magnetic flux across area phi is equal to magnetic induction into area, which is equal to B dot L into X. This is area. If suppose wire is moved, with velocity phi, then according to Faraday's law, magnitude of induced EMF, if wire BC is moved with velocity phi, then an induced EMF is nothing but minus d phi by dt if wire BC is moved with velocity phi. If wire BC is moved with velocity phi, then induced EMF due to change in magnetic flux is equal to minus d phi by dt, which is equal to minus d by dt B into L into X. magnetic induction constant है, length constant है, and therefore minus BL into dx by dt. Rate of change of displacement is nothing but velocity, therefore E is equal to minus BL into phi. Suppose this is equation number 1. This is induced EMF. In that conductor. इथं आपण पाहतोय ट्रान्सलेशनल मोशन ऑफ कंडक्टर. Translational motion of conductor. Translational motion of conductor. Induced EMF minus BL into V. If suppose charge Q flows through wire of length L with velocity phi in uniform magnetic field B. If suppose charge Q flows through wire of length L with velocity phi in magnetic field, then force acting on wire, that is Q into phi cross B, which is equal to Q phi B sin theta. This is force due to that charge, and therefore work done per unit charge work done per unit charge is nothing but induced EMF. Therefore, induced EMF is equal to work done per unit charge. What is meant by work? That is force into displacement. Force into displacement divided by Q, which is equal to force QVB sin theta divided by Q. Q like Q cancel into L. Therefore, it becomes B L V into sin theta. Since maximum value of sin theta is 1, maximum EMF E max is equal to BLV. This is maximum induced EMF. This is maximum induced EMF due to translational motion of conductor. Thus, from this equation, suppose this is our equation number 2. From equations 1 and 2, region where magnetic field is changing with time, electric field is generated. Okay. This is about translational motion of conductor. पहिले काय काढलं आपण? Induced EMF due to motion of conductor. Same induced EMF due to charge. From these two equations, whenever there is change in magnetic field, an EMF induces in this conductor. Now one more term, rotational motion of conductor. Rotational motion of conductor. Rotational motion of conductor. Suppose this one as a conductor. Suppose this one as a conductor of length L. Suppose this one as a conductor of length L, rotating in uniform magnetic field. Suppose this one as a uniform magnetic field. Suppose this one as uniform magnetic field. Suppose this one as a uniform magnetic field like this. Suppose this one as a uniform magnetic field. Consider a conductor rotating about pivot axis. Consider a conductor rotating about an axis, passes through one end phenomena in uniform magnetic field. Suppose this one as conductor rotating about an axis, passes through one end in uniform magnetic field. Let's suppose dr be the small length of conductor at distance r from axis of rotation. Let dr be the small element of conductor at distance r from axis of rotation, rotating with velocity v. Let L, that is length of conductor, dr, length of small element of conductor, r, that is distance of element from axis of rotation, phi, that is velocity of conductor, rotating velocity फारता म्हणा, rotating velocity of conductor, then induced EMF, then induced EMF is equal to, what is induced EMF? B into phi into dr. Induced EMF, small induced EMF, B phi into dr, and hence total induced EMF E is equal to integration of dE, which is equal to integration of B phi into dr, B phi into dr from 0 to L. Here phi is equal to r omega. Therefore, we can write integration of B into r omega into dr from 0 to L. B omega constant. Integration of r, that is r square by 2 from 0 to L, which is equal to half 1/2 constant B omega L square. This is an expression for induced EMF due to rotating bar, motional EMF in rotating bar. म्हणजे आता आपण काय काय पाहिजे नेमकं या ठिकाणी, induced EMF due to flux of field, induced EMF due to translational motion of conductor, induced EMF due to rotational motion of conductor. Translational motion BL phi, rotational motion 1/2 B omega L square, omega that is angular velocity. Okay, this is about motional electromagnetic field. Remaining part on next period.